Data-Driven Grasping by Corey Goldfeder and Peter Allen of the Columbia University Robotics Group. Data-driven grasping is the idea that robotic grasping can be indexed by shape. As with any data-driven method, we need a large set of example data. We begin by building the Columbia Grasp database. In previous work, we have proposed the concept of eigengrasps, a low-dimensional grasping subspace derived from human grasping experiments that has proven useful for grasp planning. Searching this subspace with simulated annealing allows us to find form closure grasps for arbitrary objects using a range of robotic hands. We used eigengrasps to build the Columbia Grasp database. The database consists of several 100,000 simulated grasps for thousands of 3D models using a variety of robotic hands. We can plan grasps for novel objects by matching sensor data into the grasp database, finding similar models, and reusing the grasps that were found for those models. The advantage of this approach is that it works even with limited or occluded sensor data, as long as we can find an appropriate match. In this example, our sensor is a standard webcam. The robot collects images from a small number of viewpoints. Our partial shape matching and alignment methods, described in detail in the paper, allow the robot to find a similar model from the database and align its scale and pose with the real object on the table. An appropriate grasp is selected, taking into account both forward kinematics and the quality of the grasps in the database. The robot then executes this grasp. Note that this is indeed the same grasp as from the database. The grasp succeeds because objects with similar shapes can be grasped in the same way. Here, we are using the same method to grasp a toy car. This experiment, grasping a glove, shows that although we do not model deformable objects, we can handle them if the deformations are small. We can successfully grasp a controller despite the fact that no controller objects exist in our database, because objects with similar shapes do exist. We are also not limited to objects that are smaller than the hand. In this example, we are grasping a ukulele, which is substantially larger than the robotic hand. Finally, we present the failure case. In this example, our assumptions about the material properties of the cone object were incorrect, and the grasp fails due to insufficient frictional forces.